talk a little bit about the Nobel Prize in Physics this year? What it was awarded for, and some of the findings with the black hole.
Sure. To tell you the truth, I've been waiting year after year for this award to be announced. It was just a question of when, and it finally happened. I went to bed the night before thinking I'm going to wake up early again this year, just like I've done year after year. Woke up early and heard the news, and I immediately emailed one of the Nobel Prize winners who I've worked with before. So this award this year was given to three people. It's always three people. Half the award was given to Sir Roger Penrose for his foundational work on establishing the theoretical framework for black holes. So general relativity, Einstein's general relativity, predicts black holes, and Roger Penrose is the one who established that connection in 1965. So it's been a long time. But Nobel Prizes usually aren't given until someone observes proof of a theory. And so the other half of the Nobel Prize this year is split equally between Reinhard Genzel and Andrea Ghez, who each led a research program to establish that there's a supermassive black hole in the center of our galaxy. I was at UCLA at the time when Andrea was hired and she started that project. It was using the Keck Observatory, which I also had used, and it was patterned after the experiment that Reinhard Genzel had established in Germany. And so Reinhard Genzel, the director of the Max Planck Institute, did this project measuring the speeds of stars in the center of the galaxy, finding that there must be a huge amount of mass in the center, because the only way to get things flying around a common point is if there's a bunch of mass in the center due to gravity. And so he did that experiment, and the UCLA group verified it, confirmed it, and year by year, they got better and better measurements. And finally, it got to the point where everyone agreed that there's no way there could be that much mass unless it was a super massive black hole.
Yeah, right. And so, um, was it? Because I remember there was the big news when the first image came out of the black hole. Was that last year or 2 years ago? Or
So that's interesting that you bring that up, because I also had thought maybe they would throw that into the Nobel Prize,
Hmm.
and they didn't. So that was taken with something called the Event Horizon Telescope, which is just a string of radio telescopes that already existed that are connected together electronically. And they took a picture of a dark splotch at the center of M87, a nearby galaxy. And that dark splotch was taken as proof positive that there's a supermassive black hole in that galaxy. They didn't award that. So I don't know if that'll be another award. Um, but they just used the black hole at the center of our galaxy for this year's award.
Mhm. Yeah, so it feels like the Nobel Prize really kind of seals the fact that we're very confident that this is what's going on in the center of the galaxy, and we're just going to continue to study it more, kind of.
Yeah, so the laws of physics are a bit crazy near a black hole, and the predictions are different than we would predict in lower gravity environments, like where we live. It's lower gravity here. But if you've seen, there have been movies that have shown this, right? Like Interstellar, I think. Then you see that there's time dilation and there's something called gravitational redshifting. So if you want to test those theories, you need an experiment that takes place where the gravitational field is strong. And that's hard to just create, right? And so one thing you have to do is just look around the universe to where that exists and do your experiment there. So what the two groups are doing now, Genzel and Gez, they're looking at objects that get really close to the black hole. When I say objects, I mean stars and gas. And they look at the motions and see if the motions are predicted by Newtonian laws or laws of relativity. And it looks like in every case where there's a distinction, it's the relativistic laws that give the right prediction, which means Einstein is right. And
Hmm.
so I think those are the kinds of experiments that are going to continue, just further validation of Einstein's laws.
Cool. And so you kind of talked a little bit about it already, but what are some of your initial thoughts when you saw the award? You were obviously excited, and was it kind of football player that should have been in the Hall of Fame. It took them too long to get there, kind of thing.
Oh, no. I think it's about the right amount of time. It's sort of maybe 10 years after most astronomers in the field agreed that the result was right. So usually you want to wait a little while just in case there's something out of left field, that comes in and throws it in a tizzy there. In the early days, it wasn't always clear. In fact, I did work that showed that their initial estimates of the mass was wrong by a factor of two. They had said that the mass was 2 million solar masses. It's 4 million solar masses. And the reason they estimated it is they interpreted the locations of the stars going around the center in a way that wasn't correct. They thought that the stars zipping around the center were near the black hole, but it turns out that they were sort of far away like this.
Mm,
So if things are zipping around super fast and they're far away, that means the mass must be even higher, right? So they
sure.
measured the velocities and the stars are far away. And so therefore the supermassive black hole has a mass of 4 million solar masses. And that's a paper that I had published, I think in 2003. So it takes a while for people to bicker back and forth, in a healthy way, and for the field to get advanced. And they went on making far more precise measurements in the end, and it turns out to be a 4 million solar mass black hole.
Right, and so they get all this information combined together, and then this Nobel Prize is issued, and so it's kind of on like the body of work, right, for these people that they get the Nobel Prize, or is there like one specific paper that they kind of point toward?
Well, so some people get the Nobel Prize because of their contributions to the field, meaning contributions over a prolonged period of time in a bunch of different areas. That does happen now and then. I guess more typically, the Nobel Prize is given for a single measurement or single theory, like the Nobel Prize given to Adam Rees and Saul Perlmutter and Brian Schmidt for their discovery of dark energy. That was given for one result, and in this case, it was given for one result: the measurement of the supermassive black hole in the galactic center and the theory. Uh, but the measurement, quote unquote measurement, didn't happen one day. And here's why. As I just said, it has to do with the speed of stars going around an object, right? Going around the black hole. How do you measure the speed of a star? What you might do is take a picture, and then a few years later, take a picture, and a few years later, take a picture, and then a picture as it's going around. And you could imagine it's going to take a while to get a complete orbit. And once you have a complete orbit, then you have the best mass. Okay. So the discovery didn't happen just one day because it can't. So it happened over a period of taking pictures uh, for about 10 years or so. And every time they got another data point, the estimate got better and better and better.
Mm, cool, cool. Um, uh, you want to talk a little bit about maybe you kind of mentioned already how you were able to work with some of these scientists and figure out the mass of this black hole.
Yeah.
What's some other stuff that you've been doing, I guess, kind of with this research?
Well, one other connection that I'll make is at the time that they were looking at the stars around the supermassive black hole, I was looking at stars a little bit further away, still in the galactic center, but further away. And the reason I did that is because the overriding theory at the time was that there are a bunch of weird stars around the black hole because the black hole makes them look weird and makes them do weird things. Okay, so everyone was looking at those stars, and then I said, aha, I'm not going to look at those stars. I'm going to look a little bit further away, and if I find stars that are just as weird, then it can't be the black hole that's making stars look weird in the very center. And so it turns out I found all sorts of stars that were supermassive and very odd, a little bit further away from the black hole, showing that it wasn't the black hole that was making them look weird. One of those stars, by the way, is called the Pistol Star. And I published the um, paper which claimed that the Pistol Star is one of the most massive in the universe, I think in 97. And in order to do that, it's important to show that the star is actually just one star. And what you do is you measure the light and say, oh, there's so much light, it's got to be really massive. But if it's composed of two or three stars, then it's the sum of the stars that's making up all the light. It's not a single massive star, right? So one of the things you have to do is show that it's single. And there was a new faculty member at UCLA who was working on a technique that she had gotten from Caltech to measure if stars are single. And so I asked her to make that measurement for me based on data I got, and she did. So that's Andrea Ghez. So she was on the paper that I wrote about the pistol star 20 years ago or 23 years ago. So my interest is in massive stars, massive star evolution, massive star clusters, and I look at the galactic center because it's full of massive stars and massive star clusters. And
Right.
so that's what I've been doing, and I continue to do that.
Cool. Very cool. Great. Um, okay, I think that's pretty good. Is there anything else you might want to add about this?
There's a piece that's kind of cool in that the Nobel Prize was directly enabled by advanced technology that Reinhard Genzel developed himself with his group and used at the European Southern Observatory at the Very Large Telescope, as they call it, the Very Large Telescope. And and that's also true with Andrea Ghez. She used cutting edge instrumentation at the Keck Observatory, some of which I developed. So I was an optical designer on the near infrared spectrograph at Keck, which they've used in part to make this discovery. So it's the people who do the observations, but also the people who are developing the technology that makes the observations possible. So I think that's a neat aspect of it.
Yeah, it seems like sure it might have just been three people, but those people it's such a collaborative effort it seems like between, so many scientists.
Yeah, and I think that the three people stand as sort of symbols of the greater achievement. And they certainly made the most important contributions maybe to the discovery, but they wouldn't have been able to do that actually without a bunch of other people.